Hi everyone, Mr. J here. Thanks for tuning in to another episode of Chem Talks. Today we are going to talk about pH. We introduced it a little bit earlier, but today we're going to look at it in a little more in depth and figure out how to do some calculations. So as we go along, please take some good notes so you have them for reference later. Okay, first of all, what is pH? We talked about it the other day, but remember, pH is simply a method of reporting the hydrogen ion concentration in a solution. Okay? pH stands for the power of the hydrogen ion. And it's based, as we talked about before, on a logarithmic scale, which has a base power of 10. What this means for us is that as we go from one pH to the next, it's not one difference, but it's 10 times difference. Either greater as we go down the pH scale closer to 1, or less as we go up the pH scale. So a pH of 1 differs from a pH of 2 by a factor of 10. It means it has 10 times more hydrogen ions in a pH of 1 than it does of 2. So as the pH decreases as we get closer to 0, the hydrogen ion is actually increasing. This is a point of confusion for some students sometimes, so make sure you keep that straight. As we decrease the pH value, we increase the hydrogen ion concentration. So today we're going to learn how to calculate the pH. And the equation for it is pH is equal to the negative log of the hydrogen ion concentration. So for some of you, this may be the first time you've seen logs and worked with them. So if you're having problems with this after the video, come see me and we'll help you. Okay? Remember, those concentration means those brackets mean the concentration of the hydrogen ion. So we'll have to be able to figure out that. So example, if the hydrogen ion concentration is 1 times 10 to the negative 10th, to figure it out, what we're going to do is take the negative log of 1 times 10 to the negative 10th, and that will give us the actual pH value, which in this case is 10. So, okay. Another example, if we have a concentration of 1.8 times 10 to the negative 5th, we're going to take the negative log of 1.8 times 10 to the negative 5th and end up with a pH of 4.74, or an acidic solution, where our previous example was basic because its pH is greater than 10. Okay, so here's an example. Find the pH of a solution with a hydrogen ion concentration, or that's actually H3O plus, is what we call the hydronium ion. The hydronium ion and the hydrogen ion are interchangeable. We look them at the same way, so don't let the H3O plus throw you. So what we need to do then is take the negative log of 1.0 times 10 to the negative 3. Okay, and the way you're going to do this on your calculator, if you have one of the TI versions, this is pretty much how we're going to work through it. If you have a different one and you can't figure it out, come see me. So first thing you want to do on your calculator is to hit negative and then your log. Generally on the TI, it's going to be on your left-hand side. Once you hit the negative log, you get a parentheses, and you're going to enter the concentration of the hydrogen ion, which is 1.0 times 10 to the negative 3. And you do this by entering 1, then hit your EE, which is often a second button. It's on mine, it's the second above the comma, and then hit 3. Okay? And by hitting the EE, it's going to mean times 10 to the negative 3. So if we look at it on a calculator, what I'm going to do is I'm going to hit the negative sign and then the log. Okay? Then I'm going to hit 1.0 and then hit second. And then here's my EE button right here. When I do that, I'll hit negative 3. So on your calculator, it should give you something that looks like this. Then I'm going to hit my enter button and I get a pH of 3. This is one reason I want you bringing your calculators to class so you can practice with this. You can't use your cell phones on the test, so you need to bring your calculator. So please be bringing your calculator to class every day. All right, let me have you try this one on your own. Go ahead and pause the video now, enter this into your calculator, and then when you're done, come back for the answer. All right, hopefully you did it. If you haven't, pause it now. I know some of you are slacking, just waiting for the answer. I want you to do it. Okay, so we're going to hit pH is equal to negative log of 1.23 times 10 to the negative 5th. Okay, you should get a pH of 4.910. So hopefully that's pretty easy for you. If you're having problems, once again, come see me. Now, we oftentimes aren't actually given the hydrogen ion concentration. Instead, we're given the molarity of our substance. And something like this. What is the pH of 0.1 molar HCl? Well, if you remember, HCl is one of our 6 strong acids that you need to memorize. And what makes something a strong acid is that it disassociates or breaks apart 100%. And since our subscripts on HCl are both 1 and 1, what we find out is that when it breaks apart, we're going to end up with 0.1 molar H plus and 0.1 molar Cl minus. Well, we can ignore the Cl minus for right now because we don't really care about it. What we do care about is the concentration of the hydrogen ion. So what we see is the concentration of our strong acids is equal to the concentration of the hydrogen ion. So that means that to find the pH, we're just going to take the negative log of 0.1 molar HCl and end up with a pH of 1.0. We can do the same thing for bases, okay, as well, because a strong base, which is anything from group 1 and 2 with hydroxide, is also going to break apart 100%. So go ahead and try this one on your own. Pause the video and come back when you're done. Okay, so HNO3 is another one of our strong acids, so that means the hydrogen concentration is going to be equal to 2.3 times 10 to the negative 3, or I should say the hydrogen ion concentration. And so we just take the negative log of 2.3 times 10 to the negative 3 and end up with a pH of 2.64. So pretty easy. We're only going to worry about strong acids. We won't worry about weak acids or weak bases, just strong acids and strong bases. Okay, now we can also solve for the hydrogen ion concentration. We know for the find pH, it's the negative log of the hydrogen. But if we want to solve for this, we can just manipulate the equation a little bit. Okay, so first thing we're going to do is move the negative to the other side. And how do we get rid of log? Well, to do that, we're going to take the antilog, which is 10 to the x on your calculator. And generally, it's the second function of your log. Okay, so this then becomes 10 to the negative pH is equal to your hydrogen ion concentration. So if you're given the pH value, you can easily find the concentration of the hydrogen ion. To find the antilog on your calculator, once again, look for this. It's going to be generally a shift second function on my calculator. It's the second function over the log. So I'm going to hit second, and then right here above the log is my 10x button. Okay. And remember, it's a negative. It's 10x negative pH. So a solution has a pH of 8.5. What's the molarity of the hydrogen ion concentration? Well, we know pH is equal to neg, so we're going to take 8.5 is equal to negative log your hydrogen ion concentration. And so we take the antilog, the negative antilog of this, and we find out we have a hydrogen ion concentration of 3.16 times 10 to the negative 9th. So if you don't have one of the nice, easy TI type calculators and you have another one, bring it up to me and we'll help you figure this. Some calculators actually have an anti-log button rather than having to do a second on it. So take a look at that. Once again, this is why you want to be bringing this. Try this one on your own. Coca-Cola has a pH of 3.12. Calculate the hydrogen ion concentration. So go ahead and pause the video and figure this out. Come back when you're done. All right, so we need to take the antilog of negative 3.12. When we do that, we find it has a hydrogen ion concentration 7.59 times 10 to the negative 4th. Hopefully this is pretty easy for you. Now we can do the similar thing for bases, but since bases, what we end up finding for bases is what we call the POH. Okay, since it's the opposite of an acid, we can find the POH. Okay, now in reality, POH doesn't exist. We don't really measure the concentration of the hydrogen ion, but it's useful for changing bases in the pH. It makes, as you'll see in these next calculations, it makes things really easy. So pH looks at the perspective from the bases side, not the acid side. And so it's the same basic calculations. pOH is the negative log of the hydroxide concentration. Or if we want to find the hydroxide concentration, we can just do the anti-log of this like we did earlier. And one extension we can make of this is that since pH and OH are at opposite ends of the spectrum, they add together to equal 14. So pH plus pOH is equal to 14. And so if we find the pOH, we can then subtract it from 14 to find the pH, which is often what we're looking for. So let's take a look at this problem. What is the pH of a 0.001 molar sodium hydroxide solution? Well, what we see then is that sodium hydroxide is a strong base, so it's going to be 100% ionized. Okay? So the first thing we need to do is find the hydroxide concentration. Well, we know it's 100% ionized, so the OH concentration is going to be equal to that of the NaOH, which is 0.001. Step 2 then, we're going to calculate the pOH, so we're going to take the negative log of that value, and we come up with a pOH of 3. But the problem is asking for the pH. So what we need to do here then is subtract the pOH from 14, and that'll give us the pH. So in this case, what we're going to see is that the pH is equal to 11. So it's an easy way to figure out the pH of a base. And since it is a base, we should expect our pH to be greater than 7, which it is. Okay, let's try another one here. What's the pH of a solution at 25 degrees where the OH concentration is 2.35 times 10 to the negative third? Why don't you see if you can try this one on your own, pause it, and then come back to me. All right, hopefully you did it and aren't cheating again. So once again, it's a strong, they give us the hydroxide concentration, so we take the negative log of that and get a pOH of 2.63. So to figure out the pH, all we have to do is subtract that value from 14 and end up with 11.37. Once again, since we're dealing with a basic solution, we see 11.3 is where we need to be. Okay, try this one again on your own. What's the pH of a solution where the hydrogen concentration is 1.0 times 10 to the negative fourth? And then also figure out what is the pOH. So pause it and then come back and just when you're done. All right, so since they gave us the hydrogen ion concentration, we can go ahead and figure out the pH right away, right? pH is just the negative log of our hydrogen ion concentration, which becomes 4. Well, we know that pH plus pOH is equal to 14. So if we take 14 minus 4, we get a pOH of 10. It's a pretty simple way there. Go ahead and try another one on your own here. So a chemist dilutes a concentrated hydrochloric acid to make two solutions, a 3.0 molar and a 0.0024 molar. I want you to calculate the hydrogen ion concentration, or the hydronium ion concentration, which is the same as hydrogen ion, the pH, the OH concentration, and the pOH of the solutions at 25 degrees Celsius. So pause this, do both of them, and then come back. All right, let's look at the first one here, where we're doing 0.3 molar of hydrochloric acid. Once again, hydrochloric is one of your 6 strong acids, so we know that the hydronium, the hydrogen ion concentration, is going to be equal to the molarity. It's 3 molar. So to find the pH of that, we're just going to take the negative log of 3, which gives us a pH of negative 0.48. So this is really acidic. Okay. Well, once we know the pH, we can go ahead and figure out a couple other things. We know pH plus pOH equals 14. So pOH is going to be 14 minus, it's a negative 0.48. So the pOH of this is 14.48. All right. And then once we know the pOH, we can take the anti-log of that and end up with our OH concentration, which is 3.2 times 10 to the negative 15. A really, really small amount. Okay, let's look at part 2, where we have a 0.0024 molar. Same thing, we know it's 100% dissociation, so we take the negative log of 0.0024 and give us our pH. Okay, it's a really small value, so our pH is much larger than it was last time, right? We're almost 3 steps up, so it's 1,000 times less hydrogen ion concentration. But once we know the pH, we can subtract that from 14 to get our pOH, so it's 11.38, and then take the antilog of 11.38 to get our hydroxide concentration, which is 4.2 times 10 to the negative 12. All right, if you have any questions on these, make sure you come see me. We'll do some more practice in class. Okay, let's take a moment to talk about water. We've talked about water a couple times in here in its special properties. And what we see, water does something what we call autoionization. Autoionization is where you have a reaction between molecules of the same substance that end up producing ions. Okay, so what we see when we talk about water is water can function as both an acid and a base. If we look at this diagram here, what we see, we have 2 water molecules, okay, and they form a hydronium ion and a hydroxide. Well, how'd they get this? Well, one of these molecules is going to donate a hydrogen, which is the white, to form the H3. If you donate a hydrogen ion, remember, you're going to be a acid or an acid. The other one, once it's donate, the other one is going to accept the hydrogen here. So it accepted it here, this one becomes a base because it's accepting. This one, once it loses, turns into OH. So this is our conjugate base here. And here is our conjugate acid because, once again, it can donate. So water can act as an acid base. If we write the equation for that, it's this top one. 2 hydrogens going to the hydronium and the hydroxide. We can simplify that down and just look at the hydrogen ion, and we can see that water can produce both the H plus and the OH. So it's acting as an acid and a base. So what we get from this, we can get what's called an autoionization constant. For water, if it's at 25 degrees Celsius, the temperature is important, okay? We can get what's called the autoionization constant, or the Kw, okay? In pure water, as we talked about, I think earlier, that the hydrogen ion concentration is equal to the hydroxide. So we get a pure water, we get a pH of 7 because it's neutral there in the center. So Kw, okay, our autoionization is equal to the concentration of hydrogen ion times the concentration of hydroxide. And at neutral, they're both equal to 1.0 times 10 to the negative 7th. So our Kw value, what we call the autoionization value, is equal to 1.0 times 10 to the negative 14th. This is a number you're going to want to remember and have memorized. And so what we can do is set up another mathematical equation. And that is that the Kw is equal to hydrogen ion concentration times the hydroxide concentration, where Kw, the constant value, is equal to 1.0 times 10 to the negative 14th. So what this allows us to do is to solve for either the hydroxide or concentration or the hydronium ion concentration at 25 degrees Celsius. And this is helpful for figuring out, once we know either of these, we can figure out the pH or the pOH. So let's look at a couple problems. Calculate the hydroxide ion concentration for a solution where the hydrogen ion concentration is 1.0 times 10 to the negative 6. So to figure out the hydroxide concentration, we're going to use that Kw value. Remember, Kw is equal to hydrogen ion concentration times hydroxide. Well, we know Kw, that's our constant, 1.0 times 10 to the negative 4th, and they give us the hydrogen ion concentration of 1.0 times 10 to the negative 6. So if we substitute here, okay, we get this. And to solve for hydroxide, all we got to do is divide the left side by 1.0 times 10 to the negative 6. And we get a hydroxide concentration of 1.0 times 10 to the negative 8th. So that's a useful way to do this, or to use that Kw value. Let me have you try this one on your own. Go ahead, pause the video, and then once you get an answer, come back and talk to me and listen to this. All right, so this case, we know the pH of 4.5. Once we know the pH of 4.5, we can take the antilog of that to figure out the hydrogen ion concentration. So I'm actually going to show you 2 methods that you can use to do this. The first one is we take the antilog of the hydroxide, which we get a hydrogen ion concentration of 3.6 times 10 to the negative fifth. So to find the hydroxide concentration, we can use our Kw value again. Okay, and so we just substitute that 1.0 times 10 to the negative 14th for Kw, and then we figured out what the hydrogen ion concentration is in here. And so we get a hydroxide concentration of 3.16 times 10 to the negative 10th. Okay, the second method, which a lot of times I find students like this a little better. First of all, we know the pH is 4.5. Well, if we know the pH, we can easily find the pOH just by doing a little subtraction. So we can take 14 minus 4.5 and get a pOH of 9.5. Okay? Well, once we know the pH, we can take the antilog of that to find the hydroxide concentration. So notice both of these are the same way. I don't care which method you use. A lot of times I think students find method 2 a lot easier, but you should be familiar with both of them based on what information you are given. So either method works. Find what you like and know it well, but be familiar with the other one as well. All right, guys, a quick review of this. Remember, pH is equal to the negative log of the hydrogen ion concentration. pOH is equal to the negative log of the hydroxide ion concentration. And then pH plus pOH is equal to 14 based on our scale, right? And then we also know from the autoionization constant that the hydrogen ion concentration times the hydroxide is equal to 1.0 times 10 to the negative 14. And we can use that to figure out either hydrogen ion concentration or hydroxide. And then remember, an acid has a pH of less than 7, so the hydroxide concentration is going to be less than the hydrogen ion concentration. Neutral, they're equal to each other, right? So they both have equal concentration of 1.0 times 10 to the negative 7. And then a base, we have a bigger hydroxide concentration than hydrogen ion concentration. Our pH is going to be greater than 7. All right, guys, thanks for listening today. We will go over some practice problems in class. If you have any questions before then, please stop in and talk to me, and we'll talk to you next time. Take care.